After age 50, the average adult loses between 1 and 2% of their muscle mass each year. By 65, estimates suggest that some individuals have lost up to 30% of the skeletal muscle they had in their 30s. This condition, called sarcopenia, is associated with falls, fractures, loss of independence, and in advanced cases, increased mortality. A pooled analysis of 11 population cohort studies with 80,306 adults found that even 1 or 2 sessions of resistance exercise per week was associated with a 21% lower all-cause mortality risk. Crucially, this effect was independent of aerobic exercise. The two forms of physical activity appear to operate through different biological pathways, which means aerobic exercise alone may not be enough. In this video, what the research on muscle loss after 55 actually shows, the key findings from the Stamataki's pooled cohort analysis, how the combination of resistance and aerobic exercise compares to either alone, and 3 practical takeaways grounded in the evidence. Quick note before we continue, this is educational content based on published research, not medical advice. Talk to your physician before starting a strength training program, particularly if you have cardiovascular conditions, joint problems, or osteoporosis. Medical clearance matters before significantly changing exercise type or load. Now, the study. Sarcopenia is the progressive loss of muscle mass and strength that accompanies aging. In 2019, the European Working Group on Sarcopenia in Older People published a revised consensus definition, led by Cruz-Gentoft and colleagues in the journal Age and Aging. Sarcopenia is now formally defined as the combination of low muscle strength, specifically hand grip strength as the primary indicator, plus low muscle mass or quantity. Physical performance, such as gait speed, is used to assess severity. By this definition, studies estimate that between 10 and 27% of adults over 60 have sarcopenia, rising to over 50% in adults over 80. The mechanisms behind age-related muscle loss are well characterized. Protein synthesis rates in muscle tissue begin declining measurably in the 5th decade of life. The motor unit, the combination of a motor nerve and the muscle fibers it controls, is lost progressively with age, and the remaining motor units become less efficient. Anabolic hormone levels, including testosterone, estrogen, and insulin-like growth factor 1, decline. Chronic low-grade inflammation, sometimes called inflammaging, creates a catabolic environment. These changes are not fully reversible. But the research consistently shows that resistance training can slow the rate of muscle loss and in many cases partially restore muscle function even in adults well past 60. The Stamatakis et al. Paper, published in the American Journal of Epidemiology in 2018, took a different approach from most exercise and mortality research. Rather than focusing on aerobic activity, the researchers specifically examined the independent contribution of strength-promoting exercise. They pooled individual participant data from 11 population cohort studies drawn from Australia, the United States, and the United Kingdom. The combined sample was 80,306 adults. Strength-promoting exercise was defined by self-report as any activity specifically performed to improve muscular strength, including weightlifting, resistance band exercises, bodyweight training, or functional strength activities such as yoga. The primary analysis compared all-cause mortality, cardiovascular disease mortality, and cancer-specific mortality across 3 groups: people doing neither aerobic nor strength exercise, people doing aerobic exercise only, people doing strength exercise only, and people doing both. Adjustments were made for age, sex, body mass index, smoking, alcohol consumption, physical limitations, and prior diagnosis of cardiovascular disease or cancer. Mortality was tracked through national death registries linked to each cohort. The results. People reporting any strength-promoting exercise had a hazard ratio of 0.79 for all-cause mortality compared to those doing neither form of exercise. That is a 21% lower mortality risk, with a 95% confidence interval of 0.70 to 0.89. The finding was statistically significant. Importantly, this association remained significant after statistically adjusting for the amount of aerobic exercise participants also performed. The benefit of strength training appeared to be independent of aerobic activity, not simply a marker of generally active people. The group doing both aerobic and strength exercise showed the largest mortality reduction. Their hazard ratio was 0.67 compared to the entirely sedentary reference group, representing approximately a 33% lower mortality risk. This dose-response pattern, with aerobic only and strength only each showing benefit, and the combination showing the greatest benefit, is consistent with the biological rationale that these two forms of exercise act through at least partially distinct physiological mechanisms. Aerobic exercise primarily benefits the cardiovascular system, mitochondrial function, and metabolic regulation. Resistance exercise primarily preserves muscle mass, bone density, and neuromuscular function. The frequency analysis in the Stamatakis paper is particularly relevant for this age group. The benefit associated with strength exercise was statistically significant at even 1 to 2 sessions per week. The hazard ratio for 1 to 2 weekly sessions was approximately 0.8, similar to the overall group average. This suggests that meaningful mortality benefit may not require daily or near-daily strength sessions. Twice per week, the minimum recommended frequency in most clinical exercise guidelines for this age group, appears to be sufficient to achieve significant statistical associations in this dataset. Cancer-specific mortality also showed a statistically significant lower risk in the strength exercise group, with a hazard ratio of approximately 0.78. Cardiovascular disease-specific mortality was lower, but the confidence interval was wider, making the cardiovascular finding less precise. The authors note that the cardiovascular signal may have been attenuated because aerobic exercise is a stronger and more established driver of cardiovascular risk reduction, leaving less statistical variance for strength exercise to explain independently. Limitations. First, and most important, strength exercise was self-reported. People vary substantially in what they classify as strength-promoting exercise. Someone doing one set of 10 push-ups weekly and someone doing progressive barbell training 4 days per week might both self-report as doing strength exercise, yet the physiological stimulus is vastly different. This misclassification likely attenuates the estimated benefit rather than exaggerating it. But it means the data cannot tell us much about optimal type, volume, or progression. Second, observational design. People who strength train may differ systematically from those who do not in ways the statistical adjustments cannot fully capture. Health-conscious behaviors tend to cluster together, and someone who resistance trains may also sleep better, eat more protein, and manage stress more effectively, all independently associated with better health outcomes. This residual confounding problem applies to all observational physical activity research. Third, no large randomized controlled trial of resistance training on mortality in older adults exists. Sarcopenia-relevant RCTs have tested physical function outcomes over shorter periods, but mortality as a primary endpoint in a true RCT would require a decade-long trial in a very large sample. A fourth point is that the self-report does not capture muscle mass or strength measurements. The Stamatakis study tells us about the association between the behavior of strength training and mortality. It does not directly test whether changes in muscle mass or strength mediate that association. Evidence from other studies, including the Cochrane review by Liu and Latham on progressive resistance training in older adults, confirms that consistent resistance training does improve muscle strength and physical function in adults over 60. That functional evidence complements the mortality association from Stamatakis, but they are separate lines of evidence. 3 evidence-informed takeaways. First, if you are not currently doing any resistance training, starting with 2 sessions per week is the evidence-supported minimum. You do not need a gym. Bodyweight exercises, resistance bands, or functional movements using household objects count. The goal in the first 4 to 6 weeks is not to load heavily but to establish the neural patterns and tissue tolerance for training. Falls and injury risk are real in this age group, which is why physician clearance before starting is appropriate, particularly for people with cardiovascular history, osteoporosis, or significant joint degeneration. Second, prioritize the lower body and compound movements. The lower body, specifically the quadriceps, hamstrings, and hip extensors, is where the greatest functional decline occurs with sarcopenia. Falls, a major cause of mortality and morbidity in this age group, are strongly predicted by lower body strength and balance. Movements like squat variations, step-ups, hip hinge variations, and calf raises directly address this. Upper body pressing and pulling exercises matter for shoulder function, grip strength, and postural support, but lower body compound movements are the functional priority for this population. Third, the training stimulus alone is insufficient without adequate protein intake. Muscle protein synthesis in response to resistance training requires sufficient dietary protein as a substrate. Current evidence-based guidelines for older adults, including the Prodigy Study Group recommendations, suggest that protein needs in adults over 60 are higher than the standard recommended dietary allowance, which was established for younger adults. The specific amount appropriate for any individual depends on body weight, kidney function, and overall health status. This is a conversation to have with your physician or a registered dietitian in the context of your specific situation, not a number to self-prescribe from a YouTube video. To summarize, a pooled analysis of 11 cohorts with 80,000 adults found that even 1 to 2 weekly sessions of self-reported resistance exercise were associated with a 21% lower all-cause mortality risk, independent of aerobic activity. The combination of aerobic and strength training showed approximately a 33% lower risk. This evidence adds to the established literature showing that resistance exercise slows sarcopenia and preserves physical function in adults over 55. This is educational content, not medical advice. Always consult your physician before starting a strength training program. Free biomarker guide in the description. New evidence reviews every Tuesday and Friday.